Okay, so it must be working now. Okay, so again, hello everyone. Welcome to this lecture about which will be about partial differential equations in mechanics. So, outline of this lecture. What we are going to do. First, I will talk about partial differential equations, or PDEs in short, in continuum mechanics. Why are we interested in developing special tools for solving them? Why are they so important? Particularly partial differential equations. Then one thing that is associated with them is boundary and initial conditions. We need to talk about that. Then we will introduce the family of numerical methods, one of the very basic ones, and I believe it's good to start learning this topic from finite difference methods. And we will consider an example, do some coding in MATLAB, and I will present you the first part of the assignment. So the literature which you might want to address first is your textbook of this course you are already familiar with, and the second one I added for these two lectures. It's a book by Klaus Jürgen Batte, one of the very esteemed persons in computational mechanics and in finite element analysis in particular. Finite element procedures. I like this book very much, so I think it's very good for introduction if you want to dig a little bit more into details about what I'm talking. You may look into this book. Okay, so let's dive in. I suppose you all know what are partial differential equations. I just put it here just in case as a reminder, because we will have to refer to this definition a little bit later, talking about continuum mechanics problems. So the notations, I will mostly be using the one that is highlighted with a bold font here. There are many others. You should be already familiar with them. And important thing in connection to continuum mechanics is a classification of second order partial differential equations. So if we consider a general form of second order partial differential equation for a function of two variables, we can present it like here, and depending on these coefficients a, b, and c, and calculating this quantity b squared minus ac, judging its sign, we can distinguish between elliptic, parabolic, and hyperbolic equations. It's a little bit deep on this side, it's a little bit on the math side, but it's still important for computational mechanics because there are very distinct problems that arise that are described by these types of equations, and they require different types of boundary and initial conditions, and often different numerical methods are used. So I just want you to keep this classification in mind. I will be referring to it several times in my example during this lecture. Okay, no questions so far, I suppose. Okay, that might be easy stuff. Then this is also actually easy stuff, at least if you are familiar with the basic concept of continuum mechanics. If not, then pay close attention to it. But I want to make it very clear because this is the problems that we will be considered numerically, and it's very important to understand why are they described by these equations, where do they come from, how we can derive them if we forgot something and if we are unsure about something. Rather than just referring to some book, it might be well to understand how to derive all the things on your own. Okay, so let's consider a two-dimensional steady-state heat conduction problem. I draw it here as a rectangular shape to make it simpler with boundary conditions, which we'll be talking about later. And suppose that there is one side of this area which is kept at constant temperature. I don't know, there might be some thermostatic device, maybe some flow of fluid which keeps this edge always at the same temperature. It's more or less feasible depending on the accuracy that you are looking at. Then there is one side is insulated, so there is no heat propagation across this line. And suppose there is inflow of heat from the left side and outflow of heat from the top side on my picture. And they are described by some quantities. Very cool. And quantities we use to describe them is heat flux. Just to remind, in case it's necessary, it's energy per area per unit time. So how much energy propagates across certain area per unit time. So this is what we call heat flux. So this is a little bit important because I will be talking a little bit more about this heat flux and boundary conditions associated with heat flux later. And suppose we are interested in distribution of temperature in this area. So we know these boundary conditions, we know the value of heat flux coming in here, coming out here, and we know this prescribed temperature, and here is insulation. Insulation, by the way, in heat propagation problems is equivalent to symmetry condition. So you can as well consider that there is a symmetric part of this structure on the downside of this x-axis. Okay, so the general approach in how we do it in continuum mechanics, we take a very small element, we call it usually differential element of this structure. And since we are interested in a steady state problem, a steady state means that nothing changes with time, so it's something steady, something that's not changing in time. So it means that any piece of matter here inside this thing must be in equilibrium in terms of how much heat comes in, the same amount must come out. And so I draw this very small element with sides denoted by dx and dy to make it easily compatible with differential calculus. And so there is some heat going in this side of this piece of matter, going out here, and same here and here. It doesn't matter actually where it goes in and where it goes out. I used here these directions just because of positive directions of my axis. Okay, it might be negative, so if this value is negative, then it means that actually it doesn't come out. And okay, so you get the idea. And we write this balance. So everything that comes in plus everything that comes out with opposite sign, obviously, must add up to 0. Okay? Nothing complicated so far. Now we just use these partial derivatives here. Because if this is, I repeated here, the same balance equation, and if the first term, if we divide it by dy and multiply by dy, nothing changes. We do the same with dx. And if we look carefully at this picture and this expression, we realize that it's nothing but partial derivative of this heat flux that going through these two vertical lines with respect to this coordinate. The first term is about horizontal lines. Okay, this here and here, and this is partial derivative. So that just why I wanted to remind you the definition. So it's exactly like that. So if it's an infinitely small amount of matter, then we can express this idea of balance in terms of partial derivatives of heat flux that's propagating across boundaries across horizontal sides and qy, and across vertical sides qx. Okay, that's how it looks, this balance equation in infinitesimal quantities using derivatives notation. We still cannot do anything with that because it's just about heat flux coming in and coming out. So it doesn't tell us anything about temperature. And to tell something about temperature, we need to introduce something that in general is called constitutive equation. In this particular case of heat propagation problem, it's usually Fourier's law, and it connects heat flux with temperature. So it describes how the material behaves. So the material behaves that in response to a certain gradient of temperature, difference in temperature on different sides, there is it creates some heat flux between those sides. So if there is a difference in temperature here and here, then there is heat flux. And how strong is this heat flux? It depends on the material. There are materials with higher heat propagation and with lower heat propagation. And in the simplest form, which is actually used, I don't know, in like 95% of engineering tasks, this simplest Fourier's law for isotropic material. So this quality of the matter is described by thermal conductivity, this K coefficient. Okay, we will be programming a program of this type, actually next time with finite element methods. But yeah, so it's good if you understand what is it and can guess its dimensions, its units, and what would be a reasonable value for this thermal conductivity. But we will talk about that later also. Okay, so if I use this Fourier's law, which actually connects heat flux with gradient of temperature, and substitute it here, then I get this form of equation. And since I have 0 in the right-hand side, here I cannot care about this thermal conductivity at all. And what I get is just Laplace equation. Yeah, I suppose you are fully familiar with these type of equations and how they can be solved. There are some analytical methods, but we will not be talking about them in this lecture. We'll be talking about numerical methods. So the short way to express this is using this Laplacian operator notation, this delta symbol. So it's just Laplacian of temperature equals to 0. And from here we can find the distribution of temperature, but not yet, because you realize that there is nothing here about what happens on the boundaries, which in our case actually what defines the distribution of temperature. Otherwise, the obvious and the only solution will be just 0 temperature everywhere. So it's important that we will have to think about boundary conditions. I will talk about them in a couple of slides later, but first, if we get back to the classification of partial differential equations of second order, and I put it here again to remind you, and compare to this equation, that we see that it's an elliptic equation. Yeah? Two of the coefficients are equal to 1 and 1 is equal to 0. Okay, so we don't have this mixed derivative. So this is the simplest example of Laplace equations, where they come from, we can see them, for instance, in steady-state heat conduction problems. Other examples could be magnetostatic or electrostatic problems, or actually diffusion problem. In all those cases, we end up with this type of equation. It might be more complicated, of course. It might be non-homogeneous, have something else than 0 in the right-hand side. It would be a Poisson equation then. And in this particular problem, that would refer to the situation when there is some heat generation, internal heat generation. It might be due to different reasons, might be due to chemical reaction, might be due to joule heat generation because of electrical current passing through that structure or other things. Then we would have something else in the right hand side, and we would not be able to omit this thermal conductivity. Yeah, so it kind of makes impression that thermal conductivity is not important in steady state heat conduction problems, but actually it is. In this particular case, it will be important used in boundary conditions, but also in more general case it will be used if there is something else in the right hand side. Okay, so quite simple, I hope. What if we change it a little bit? What if we make it transient? And to keep it still within two variables, I will make it one-dimensional, actually, in this case. So I say that in this case, I formulated this way, that nothing changes along y-axis. So there is some distribution along x-axis of temperature, and boundary conditions are formulated in a way that nothing changes along y. So you may think as infinite stripe of something along y-axis, and we had heat flux on the left-hand side, and we have fixed temperature in the right-hand side. But what if, in this case, I'm not interested in a steady-state distribution? Steady state would be something that distribution that we see after infinite amount of time. But what if we are interested in evolution? For instance, there was ambient temperature everywhere in the beginning, and then we apply heat flux according to some law. Might be Heaviside function, or might be linear distribution in time, and then we, for instance, keep it constant, and it's heating up this plate or this stripe, and we are interested in how temperature is evolving in time. That actually produces a different type of differential equation according to our classification. So we use the same approach, differential element, and but the consideration about equilibrium changes a little bit, because now we don't have equilibrium, but we have kind of dynamical balance, which means that we formulate equilibrium like equilibrium quotes, like rate of heat input must be equal to the rate of heat stored in the element. And rate of heat stored in the element we described with this quantity specific heat capacity, or it's often called just specific heat. It's property of a material describing how it stores energy, thermal energy, temperature. So how much energy is required to heat it up by 1 degree. Yeah, so actually that's literally the definition, but you must add unit of mass also, or unit of volume. There are two different quantities which are of course related. Okay, so applying similar procedure, we write it this way. So using this definition of specific heat capacity, how the material stores energy. So difference between input and output heat flux is equal to the stored energy inside material, which we can describe this way, the rate of change of temperature. And again, applying the same things, so partial derivatives and Fourier's law for heat conduction, isotropic heat conduction, we end up with this type of equation. So there is one spatial variable x, but there is another variable time in this case. And in this classification, it doesn't care about what physical meaning each of the variables have. It might be time as well. So looking at this general form, we see that we get this kind of equation if we put b and c equal to 0, a equal to 1, and we have this right-hand side not equal to 0. Okay, but this right-hand side doesn't affect the type of the equation, and we see that it's a parabolic equation. So I need the right-hand side to make it meaningful, to make it produce something other than a trivial zero solution. So it's a simplest form of parabolic equation. So this is where we can see this. Okay, why zoomed in a little bit, I don't know. Okay, and the last example. I don't want to bore you to death with multiple examples from continuum mechanics. They are all very simple, but I just want to have one example for each type of equation. And then we will be talking about how to deal with them. So now I want an equation of the third hyperbolic type. So this type of equations, we often meet them in a dynamic problem, so when there is mechanical dynamics. In heat conduction, we didn't have this second derivative. Yeah, because that's a little bit of questionable subject, because currently there are some theories, which alternative heat conduction theories, developed for special applications where prediction of classical theories do not match experimental data. And actually they say also that it might be possible that this type of equation may be produced in heat conduction, that heat conduction problem might be described by this wave type equation, so there might be heat wave propagation, but that's a little bit special topic. So in classical heat conduction theory, we don't have these hyperbolic type of equations. But we have them in mechanical dynamics, in very classical. So again, to make it simple, to fit into this two variables classification, it can be extended, of course, but I just want to make things simple and clear. So I consider one-dimensional problem. So let's consider we have a bar fixed at one end, and there is a force applied on the opposite end, which stretches the bar. And it's a dynamic force, so it changes somehow in time. We might apply rapid force, some kind of shock, or we might hold it steadily, anything. And we are interested how each part or each cross-section of the bar is moving in time. So our function of interest would be a displacement u as a function of x, the only special coordinate in this case, and t, time. Again, the same principles. Surprisingly, very much we can do with this very simple idea of considering very small element and requiring it to be in equilibrium in different parts of actually physics, not only mechanics. Okay, so in this case, I will be using some quantities from mechanics. I suppose you have had some courses with strains and stresses. Which ones? Three?
We've studied quantum mechanics and all the equations about the beam, the stress and the stresses, and their equations.
Okay, so I wouldn't put it in I get the idea. Yeah, okay, so you studied what? Yeah, there are different names for this course. It's sometimes called mechanics of materials, or fundamentals of solid mechanics, or strength of materials. Yeah, but we were talking about beams. Yeah, it's not entire continuum mechanics. I can assure you, but at least you have this idea. I don't need to explain about stresses and strains. That's very fine with me. Okay, so again we consider this element and very small element of length dx. And there is some force in the left-hand side, the left side of this element, and some force on the right side. They are not equal in general case, and they are described by stress value, which is, in this simple case, it's just force. It's scalar quantity, just force by area. In a more general case, it's a second-order tensor in classical continuum mechanics. But in this case, we don't need to care about that. We have just one coordinate to one direction. Okay, and we require it to be in a dynamic equilibrium according to D'Alembert's principle, which means that if we add inertial forces into our equation, then it must work the same way as static equation would work. Okay, so this is the balance of forces accounting for inertial force, for the inertial force on the right side. Or you can think of it as this form of second Newton's law, in this case. The idea is basically the same. Okay, and again, we need to use something for constitutive equation. And there is a variety of constitutive equations used in continuum mechanics and in solid mechanics, but you are for sure familiar with this simplest, which is Hooke's law. This, I put it here for this one-dimensional case. It's in general case, it's generalized to three-dimensional case, and there might be different properties in different direction, but for the simplest case, it's just like that. We have only Young's modulus, the only property that is relevant for our problem. Now, in general case, you know that for isotropic case, you would have two quantities, for instance, Young's modulus and Poisson's ratio, or Young's modulus and shear modulus. But here we are only interested in displacements along one axis, so we don't care about anything like that. And using similar procedure, so I will not be talking longer about it, we get this kind of equation. And it's the simplest wave propagation equation. We have second partial derivative with respect to spatial coordinate, x, and we have second partial derivative with respect to time. So the typical solution of this type of equation would be, it's called wave propagation, and it describes how displacements propagate along this length of this bar. And looking at our classification, we conclude that it's a hyperbolic equation, though. This third type. And they're different, as I mentioned, because we will need different types of boundary and initial conditions, at least, but also sometimes different methods are used. If we get back to the first example, let's formulate boundary conditions. How we can do that? It's easier on the right side. We just prescribed the temperature and this coordinate with x fixed for any y is equal to the known value. For the okay, let's start with, they are all the same actually, basically all other phases in our case. So we need to describe the heat flux, and heat flux is described according to Fourier's law. It's connected with our unknown variable temperature, and using this this Fourier's law, we say that heat flux here, for instance, equals to this Q0, and I use this part, and this is what I get. So I have a imposed partial derivative of our unknown function on this left side. Similarly, I have imposed partial derivative with respect to y on this top side. And on the bottom side, it's insolation. Insolation means that there is no heat propagation across that boundary, which means that there is zero heat flux. So we can just use zero values for in this Fourier's law, and substituting according appropriate orientation, we get this partial derivative with respect to y, because this phase is orthogonal to y, and it must be equal to 0. Looks quite simple, but I want to talk a little bit more about this, because this is the moment where some confusion also often arises when people only start first things in heat conduction problems, solving them numerically. So what do you think about this heat flux? It looks like a vector, right? It's x component and y component of a vector. Yeah, it's a vector. We can use a vector to describe that. It's kind of natural thing. So what do you think about heat flux being a vector? So there is some direction involved, and do you think this type of situation is possible, where I have a phase and I have this fixed heat flux coming at certain angle inclined to that phase? What do you think about it? Does it look right, or you have any concerns? no particular concerns. If there is a vector, why not to draw an arrow to represent it, right? Okay, but you are feeling where I am going to, that there is something not right with this picture probably, because I'm asking. And that's actually a question that I had a lot from students when they start doing, for instance, solving heat conduction problems with file element methods using some commercial codes like ANSYS or Abacus, for instance. And they put boundary conditions, so there are some Windows forms to put boundary conditions, and there is no possibility to indicate the direction of this heat flux. So when I am putting a boundary condition on this side, or I know any of those sides, there is no possibility in those commercial codes to describe in which direction the heat flux is approaching this boundary. And that sometimes that confuses students. First, because it's a vector, there must be a direction. Why not to describe this situation? So there is no mistake that it's not possible, because this figure is actually incorrect. This confusion comes from the fact that we are accustomed to dealing with vectors that mean some quantity directed in space. What I mean is that if we are talking about velocity, so it has magnitude and it has direction. Where is directed? And it's clearly a vector, and no problems with that at all. Whenever we have velocity, we always specify either components of the vector, or we specify magnitude and direction. The same stands for displacement, acceleration, force. They are all vectors. They represent physical quantity that have magnitude value, and they have direction. They have kind of physical idea behind the direction. With this heat flux, it's a little bit different. We described as a vector. It's the same type of mathematical object, vector. No difference. There are a little bit different vectors called axial vectors, which we use to describe, for instance, angular velocity. There is a little bit of difference in mathematical description if you dig deep into it. But this is absolutely usual vector, or common type of vector. But we cannot do things like that, because there is no physical direction inside this vector. If you remember the definition that I put in one of the first slides, it's energy per area per time. Okay, I put here this word flow energy, that's how it propagates, because it's across some area. So energy doesn't have any direction, it's a scalar quantity. So how much energy comes through certain surface? If I already have a surface defined, some face, like this one, or this one, then the heat flux would mean how much energy comes through this surface in time. There is no room for any other direction. The only direction that is inside that this Q, this heat flux vector contains, is the direction of this area. That is important when we are talking about some points inside of our body. So if we are talking about heat flux at some point inside, then okay, to define heat flux, we must define some surface, because it's energy per area we need to define. If we consider, I don't know, some kind of inclined surface, then how much energy comes through this inclined surface in time? That would define part of this vector, or its projection on a certain direction which is perpendicular to this plane. And when we already have this, so the direction inside, the direction component inside this vector is actually area which we are looking at, across which we are calculating this energy flow, how much energy propagates across the area. There is no direction of propagation of energy. We can think about it that way, but be a little bit careful about that. So the physical meaning of the direction of this vector is the area for which we are calculating this orientation of the area. We're using normal vector, of course. So that's the reason why I put here those waved lines, not real arrows, waved lines, because actually it's scalar quantity. Once we've defined the area we are talking about, now it's scalar quantity. So that what I pictured here is not possible, because there are two directions in this picture. There is one direction defining orientation of the area, and another direction defining orientation of this vector. We have this type of structures in continuum mechanics, and you know a little bit at least about that. It's when we are talking about stress tensor, for instance, it's second order tensor, because it contains information about numerical quantities and two directions. So stresses, if we were talking about stresses, then I could draw this type of picture and said, okay, knowing the direction of a plane, I can, and knowing the stress tensor, second order tensor, I can define three components of the vector of the force which is acting on that plane. So there are two directions: direction about orientation of the plane and direction about force that is acting. And it's similar in this case, but a little bit more simple, but sometimes it causes confusion. That's why I'm talking about. So we have one direction of the plane, but what comes to this plane is not a vector, it's energy. So then it's scalar quantity. Okay, so please be careful about this vector. Don't be confused that software that you're using doesn't allow you to define direction of this vector when you're applying boundary condition, because this part is already defined by orientation of the line or whatever surface you're applying it to. Okay, so going back to other examples, this must be faster. So the second example differs with the first in having evolution of things over time. So if we are interested in how something changes in time, we naturally need to define some what was at some initial moment. So that's initial conditions. In this case, looking at mathematically at our equation, we see that there is a first derivative with respect to time, and that means that we will be happy with one initial condition. We are only able to physically in like direct problems in continuum mechanics, we are only able to define quantities at one time in the beginning of the process. We are normally not able to define something at the end of the process because we usually don't know that. So unlike boundary conditions where we define them on different boundaries, this thing we can only define it at initial point. It's usually t equal to 0, but it doesn't really matter very much. You can use a different time point, but it's just convenient to take 0 time for the beginning of your process. It doesn't affect anything. Okay, so we have less boundary conditions here, because I didn't say anything about insulation, because I kind of implied that they are already satisfied by my suggestion that nothing changes along y, the temperature changes only along x. So I'm not formulating full problem with actually all boundary condition, and we could do that and we would obtain that temperature is all the same for any y values. It only depends on x, but it's kind of obvious from our statement, so no need to do that, and we can formulate one variable, one coordinate problem, one-dimensional problem. Okay, that's why we have low amount boundary condition, but they are at two ends. Please notice that, and we have one initial condition at time equal to 0, which allows us to deal with this. Okay, this number of boundary conditions is another confusing topic. It looks obvious for this scalar quantity temperature propagation problem, because temperature is scalar, and we have second derivative, we have two boundary conditions, we have first derivative, we have one boundary condition. That's okay, it's that obvious in this case, but in more general case, it's a little bit more complicated. We'll talk about that a little bit later when we'll be talking about finite element method. Okay, so the third example differs mathematically, that we have a second derivative with respect to time here, which naturally means that we would have large amount of initial conditions. We are still able to formulate them only at time equal to 0. But in that case, we need to formulate two of them, and one would be displacement at each point, at initial time moment, time equal to 0, and second would be velocities at each time point. Okay, because those two are different conditions. We can say that initially this bar is undeformed, but at the very first moment, this initial moment, its points already have velocities. So the next moment they will move somewhere, regardless of this force, even we have no force applied. So we need velocities. Mathematically, that's because of the different type of equation, because we have second derivative, it's a hyperbolic equation. So the first elliptic was also contained two partial second derivatives, as you remember, right? But there were derivatives with respect to time. Difference between elliptic and hyperbolic types of equations, if I go to the beginning, the first one and the second one, they both require that we have two partial derivatives, but that's the sign of this quantity. So that depends on the sign of coefficients. And because time is physically in our continuum mechanics problem, it's different type of coordinate, different with respect to spatial coordinates. So because of that, in equations we have the different sign here. So these two quantities, they cannot be negative. There's density and Young modulus. They can be only positive. Otherwise we would have mathematical instability of continuum mechanics problem. So that's hyperbolic equation. It looks similar to the elliptic, but it's different. And in continuum mechanics, it's very simple. It's different because it's time. One of coordinates is time, and it makes all the difference. It makes us to use different types of conditions. We call them initial conditions, and they are different because we only can formulate them at initial time moment. We cannot formulate what was at time 0 and what was at time 10 seconds, and then deal with it as with a boundary condition problem. It is possible mathematically, but it usually doesn't make sense in describing mechanical problems. So there is some difference between time and spatial coordinates, which I'm trying to highlight, which makes this type of equation different for us than elliptic equation. Okay, so you get now the first idea about boundary and initial conditions. We'll talk about them later when we face them. Okay, no questions so far? By the way, if you have any questions, you can interrupt me anytime. You don't need to wait until I ask for questions. It's perfectly fine. We have not many people here, so it would be nice to have some kind of dialogue if you ask something or in other ways react to what you see, what you hear. Maybe you disagree with something, or maybe you have a better example in mind or something else. So you're welcome to put a comment at any point. Okay, that was a little bit of theory, just to make us make sure that we are all on the same page about that. And now actually computational methods, which is aligned with our course. And the computational methods I will be talking now is a group of a family of methods which is called finite difference methods. There is a very simple idea behind it. The idea that we replace derivatives that are present in our equations with finite differences. So we calculate derivatives numerically. That's it. So to illustrate this idea and to introduce one particular method of this family, central difference method, let's say we are talking about some body, which something changes along this horizontal axis, and I discretize it. I put certain points, some n amount of points, and I put numbers, associate numbers with those points. So there is some point in between, which with index I, and the previous one was I minus 1, and the next one is I plus 1. And I will introduce some imaginary points, some intermediate points. So they are all kind of imaginary, so they are not physical particles, not necessarily there are any physical particles there, but I will also introduce some points in between. And I will call them with this peculiar way I minus 1/2 or I plus 1/2. Okay, they are with gray, they are in between. So the distance, let's suppose the distance between points, normal points, the black ones, numbered with normal numbers is h, and therefore these gray points are in between, and it's h/2. So then how we can calculate partial derivative of some quantity u with respect to x at this intermediate point I plus 1/2. So I will be using this notation. So to make it a little bit shorter, in this particular case, I will be using these notations for partial derivatives, first partial derivative and second partial derivatives with those primes. Just not to make equations too cumbersome. So basically, first derivative, we calculate difference to the left is and to the right. So if I'm looking at this point I plus 1/2, this one, so I take the value here to the right, subtract value here to the left, and divide by the distance between two points. So that's some numerical evaluate of our derivative. Its accuracy, of course, depends on how far I take those points. If I take them infinitely small, the distance infinitely close to each other, those 2 points, then that would be precisely the derivative. Okay. So similarly, at this left gray point, I have these and these values. These were about first derivatives, and then if I want to calculate second derivative, u double prime at this central point I in my picture, then I take this first derivative to the right and first derivative to the left, calculate the difference and divide by distance between the distance between two gray points is again h, of course. Great, nothing but definition of derivative, calculating it approximately for distant points, so no limit here, and then I substitute these two expressions here, and I get this expression for second derivative. So now you can see that why I made those two intermediate points and made them with different color, because they do not appear in final expression for the second derivative. So the second derivative at this point I can be calculated according to this equation using the value of the function, unknown function at this very point, the value of this function at the point to the left, and the value of this function at the point to the right. So I need to have this grid of black points. This is my discretization. to be able to calculate derivatives. And at each point, I can calculate the second derivative according to this equation. So that's called central differential approximation, naturally because we are calculating value in the center, knowing values to the right and to the left. There are possible different types of approximations using this finite difference approach. You can easily construct them in a similar way, but this one is quite all right for our purpose today, at least. And in fact, this method is, despite its simplicity, and I'm talking about it in these very, very simple equations and simple ideas, it's actually widely used. It's not so much used currently in engineering for solving with respect to equations with respect to spatial coordinates, but it's actually used a lot for approximating time derivatives. So for time integration, for calculating dynamics, it's used a lot. It's one of the most used methods, this central different approximation in time integration. It results in so-called explicit time integration scheme, and it's used a lot in engineering and computational mechanics. So it's not something too simple that you don't need to know because it's something for kids and real people use something else. It happens sometimes, but not this case. So it's very simple, but it's used. You will face it a lot if you deal with continuum mechanics problems, especially in dynamics. Okay, so let's apply this to one of our examples. And to make it very simple, because this is where some small things come into picture, and it becomes a little bit less obvious when you need to code it yourself, and then you immediately face it looks very simple, but when you start coding, it's always like, but I didn't say anything about the endpoints. How do I satisfy boundary condition or something else? It's always some small things that you deal with when you are doing something yourself. So to deal with them in a clearly way, to explain some basic tricks behind it, I will make the problem even more simple than it was. So it's our third example about a bar, but I will make it static this time. Oh, it's so simple that you can, of course, solve it analytically. This static deformation of a bar under applied force, you can solve it analytically. Of course, no problem, but I will still be use this numerical method to illustrate the idea, and then you will be able to solve, to make it a little bit more complicated, so that you cannot at least easily solve it analytically anymore, but still are able to solve using this scheme, computational scheme. Okay, so this is our bar, and I have a force applied to the right end. What I'm interested is displacement, distribution of displacements along x. It's quite obvious what would be the result, and it's very good if you at the very beginning just look at this problem that you immediately want to tell me why would you want to solve this problem. It will result in linear distribution of displacements. What else can I give? Yes, that's true, and I encourage you to do this kind of predictions whenever you can, because it's actually it helps a lot to check your solutions when you have an intuitive prediction of how the solution must look like. That's very, very nice, because then it's so easy, especially when you are dealing with the numerical methods. It's so easy to make some silly mistake, to make some typo and get a completely wrong result, and it's very crucial to be able to see that from the first glance that, okay, this is completely wrong, I must have made some stupid mistake here, or it's here, or that's a typo. Correct, now it's correct. At least it looks correct. Maybe some further investigation is required to check if it's really right, but still. So please do that. Please try to see the solution, and you can see the solution here easily. Linear distribution, constant strains along the bar, linear distribution of displacements. Okay, but how to deal with it formally? So this is our equation, and we have boundary conditions on the left and right hands. On the left hand is prescribed displacement, and on the right hand it's prescribed force. And that is how we can deal with it, because we know that I implied here there's Hooke's law, that stresses are connected with strains. Strains in this case are just derivative with respect to x. I could have used full derivative, of course, because there is nothing except for x, but I'm using partial derivative notation to keep it consistent with other parts of our talk. So don't see too much into that, into partial derivative here. In this case, it's the same as full derivative. Okay, so strains are just a derivative of displacement with respect to x in our case, and strains are linearly dependent on stresses. Stresses are, in this simple case, is just force divided by area, so R over S. This is my stress, and it equals to Young modulus E times strain. So E times partial U over x with respect to x. And I've rewrote it in this manner that I have only this partial derivative on the left-hand side of the equation. And it's evaluated at the value x equal to L, our length of our bar. Okay, so let's say we want to test our approach. We want to test this approach, and we want to solve this problem using this central difference approximation for the second derivative in the equation, but also for the first derivative in the boundary condition. For the first derivatives, it was like that. Okay, so if I look at some intermediate point I, then second partial derivative for displacement with respect to x, according to central difference approximation, can be expressed using the value of this function in this value point I, value of this function to the right, and value of this function to the left in the neighboring points, divided by h squared, where h is the distance between our points. So I suppose that this step, I distribute them uniformly. You can easily apply this scheme for non-uniform distribution, of course, but to make things easier, for now, let's suppose it's uniformly. All points are distributed uniformly. Right, and this second partial derivative equals to 0 according to our equation. So if I put this equal that to 0, then I don't need to pay into attention to the denominator, because I have just 0 in the right hand side, and this is what I get, right? Because of this equation, because of the second derivative, then numerically values of the displacement in the 3 neighboring points must be always in this relationship. That applies to all internal points. What about our ends? So I started here this numeration from 1. So the first is already somewhere here. This is first point. This is 0 point. 0 point, I explicitly write that it equals to 0, right? Our boundary condition. What about the boundary condition on the right side? This is a little bit tricky, because I need to estimate the derivative at that point. And according to our central difference scheme, to estimate derivative, I need values to the left and to the right. I could have used a different scheme here, not central different. I could have estimated derivative using values only to the left, but there is actually no real need to it. We can stick to this central different scheme in every aspect of our problem. So let's imagine there is some imaginary point, this green one to the right. So there is no bar anymore here, there is no material, but somewhere in space, my imaginary point. Okay, and let's suppose there is some value of displacement, some fictitious displacement. And then the derivative that appears in my boundary condition of my displacement at the right end of the bar can be expressed using value to the left, value to the right, and distance between them, and it will be double our h distance between 2 points, right? And that, according to my boundary condition, must be equal to force R over E Young modulus and S cross-sectional area. From here I can express this displacement at this imaginary point using displacement of the point inside and the value of the applied force. And if I look at my set of equations, actually, which start by 1, but they must end at n, and for n I again have this u at n plus 1, u estimated here, for the last equation in this set. And I substitute here this representation of this displacement at this virtual point through our boundary condition. And then I have n equations, and which only include displacements at point 1 to so on point n. They do not include any more displacement at this point n plus 1, but they include this force boundary condition. And actually I will be talking about that a lot more in the next lecture, but you can see already here that there is a principal difference in how you treat different type of boundary conditions. Boundary conditions that are this type, prescribed displacement, and boundary conditions that are of this type, prescribed forces. There is huge difference, mathematical, between them, mathematical difference. And that mathematical difference leads to the fact that we are treating them in a very different way. So this displacement, they are actually called okay, this is a displacement boundary condition, but we can also call them essential boundary conditions. So it's more general term, which can be applied to any problems, heat conduction, magnetic problems, electrostatic problems, anything. And this is, it's also a Dirichlet boundary condition. Speaking in mathematical terms, it's Dirichlet boundary conditions. Speaking in finite element terms, it's called essential boundary conditions. And the essential boundary conditions may be not only Dirichlet boundary conditions. For some numerical schemes, derivatives may be also included in essential boundary conditions. That depends on our degrees of freedom, on our interpolation that we are using. So later about that, just to give you some understanding about terms that I will be throwing here and there. So this is essential boundary condition, and this second type is natural boundary condition. These terms, it comes from a variational statement or weak statement of problems. Again, about that we'll be talking next time. But it results, at least as you see even here, we didn't say anything about variational principles, but still there is very different ways how we impose. We just impose directly our boundary conditions for this left end, essential boundary condition, and we kind of incorporate this second type of our second boundary condition, this natural boundary condition, into our equations, numerical equations, into our numerical representation of equations. You can see that now we have this set of equations with this substituted into them, this applied force. Okay, so I summarized it here in the right side of the slide. So for I equal to 1, we have u0 equal to 0, so it's just double u sub 1 minus u sub 2 equals to 0. Then for any intermediate value we have of I, we have this equation, and for the last I equal to n, this right hand, we have this type of equation. This is where our natural boundary condition came in. Okay, this is one way how we can deal with different types of boundary conditions in finding different approximations. and I can summarize it in a matrix form. There was not much need for that, so we had this in the right hand side. The only equation that had was non-homogeneous was the last one. It had this force in the right hand side with certain multipliers, and but I put them in front of this left hand side to make it consistent with what you will get in finite elements naturally, and what you would get if you considered more general approach, more general problem, like having body forces here, for instance, applied to this problem. And this is what I will encourage you to do in your first part of the assignment. So this is a more general form. Of course, it could have been there. Mathematically, for this case, it doesn't matter, but still. So we have this multiplier. We have some kind of matrix, n by n, whereas n is our number of points, our discretization that we applied to our problem. There is this column of our known values, values of displacement at all those points where we are seeking for them. And there is this right-hand side, which in this particular case, it has all zeros except for the last element, which is our applied force. So it came into the right-hand side of our equation. This because it was a natural boundary condition. So we can present that in this classical form: Ku equals to F, matrix equation, and we can solve that for this column of unknown values U and linear set of equations, and we can find those equations at all points. And that will be our numerical solution. Okay, and that's what we are going to do right now. Do it and test it to get some little bit of hands-on experience. So please start your MATLAB. I suppose you have it here on these computers. So no fancy programming tricks here, but just as simple as it can be. So first, it's useful when you are dealing with some physical problems. It's useful to put somewhere in the beginning of your code all your set of parameters, because you might want to change them and test how results look like for different sets of parameters. And of course, it doesn't matter mathematically that you are just solving a system of linear equations. It can be whatever values. But I always encourage you to try to use some realistic values. And that's not just what looks nice. It has to do with your intuition, because using some simple test problems, you help your intuition to develop this intuition that I already mentioned, that allows you to predict solutions, at least qualitatively, how they must look like, in certain cases even quantitatively. And if you are using some random values, I know you put just 1 for Young modulus, and you put 1 billion for the force, and you have no idea how it's related, what kind of displacement you would expect. But if you apply realistic parameters, let's say we use some dimensions, the bar of dimensions that we can imagine, like 1 by 1 centimeter cross section, quite a thick bar, and of 1 meter length, and let's say it's made of steel. So I put 200 to 10 to the 9th as a Young modulus, something typical values for a steel. 200 GPa. So at ambient temperature, it's often closer to 210 GPa Young modulus of steel, but still 200 is quite a reasonable value. And then if you have something realistic, you can use your intuition to predict the answer and to set some kind of realistic force. For instance, what kind of force do I need to apply to this bar of 1 meter length and 1 by 1 centimeter cross section made of steel to produce any noticeable displacement that are not in nanometers or something even smaller that are not in kilometers, but that are, for instance, in millimeters or in centimeters, something reasonable how a bar could behave. Then you can test. So in this example, I put approximately weight of a 1,000 kilogram body. Do you think it can deform this kind of bar? If we have vertical bar and we hang 1 ton of weight on it, what kind of displacement would it produce? What's your intuition and your knowledge from mechanics of materials or solid mechanics course tells you? Is it a reasonable value of force? So 10,000 newton?
Reasonable because the tension would be of order of 10 power to 8, and then over Young's modulus, there would be a good, let's say, deformation, a strain, and so
Okay,
it sounds
fine.
okay to me.
Yeah, I also think so. But we'll check in the results. We'll see how much displacement we get, and we can. But at least if we get some kilometer displacements or some nanometer displacement, we would immediately understand that something is wrong. Something in our solution is wrong because we made parameters that were expected to produce some reasonable displacement for this type of structure.
Could you please go back to this slide that we had before modulus so that we could
Yeah. Well, I have details on the next slide also. I put here. Okay, you can use some different way to fill this matrix if you see any way that you like more. This is just very simple. So I fill in a loop. I fill all lines except first and last row, and the first and last row I put numerically. Maybe you'll see some more fancy way of filling the entire matrix. Of course, there are other ways. For instance, I would not use this type of procedure for finite element analysis, and we will deal with that later because it's actually okay. While you are talking coding, if you can listen, I will speculate about a little bit about the structure of this matrix. So it's quite a peculiar structure actually. We have this band of values on the around main diagonal of the matrix, and we have zeros everywhere else. So it's a band type matrix, and this is what the type of matrix that you typically obtain in well-defined solid mechanics problems. This was for finite difference method, but also you get this type of matrices in finite element analysis. You might not get it if it depends on how you enumerate your points. They're usually called nodes. We can call them nodes in finite difference methods as well. So how you enumerate those nodes. In this case, we had only one axis and displacement along that axis, and it was kind of natural to enumerate from the left end to the right end. But if we put numbers of those points here in a different way, let's say this is point number 1000, this is point number 1, number 2 here, this is point number 3 is here. So that would still be possible if we somehow program that sequence, put it into our problem. It would be possible, of course, to formulate those these equations and to form this matrix, but the matrix would be a disaster. A disaster because there is a difference in numerical solution. If you have this type of matrix with narrow band of non-zero values and you have nodes everywhere else, then you can use certain tricks from numerical algebra, from computational numerical algebra, how to solve this set of equations easily with less resources, with less memory required at your computer. And it helps a lot. Because of course it doesn't matter if you have 100 of points or even if you have 1,000 of points. But imagine you have 10 million of points, which is not so crazy for engineering problems. You can easily face problems where you really have to do this kind of discretization with millions of points, millions of nodes, in order to get required accuracy, the accuracy that you want to get out of this solution. It's a very possible situation. And in that case, it really doesn't matter how you deal with this set of equations afterwards, this ku equal to f. And you would like to have this matrix with as narrow band as possible to solve this problem effectively in reasonable time using the resources of your available hardware. Another thing I would like you to notice about this matrix, aside of this band structure, that it consists of this type of matrices 1, -1, -1, 1, and which overlap on diagonal elements, and those elements add up there. So that's why we can think of this matrix, at least its regular part, everything except for this first row, as a sum of small matrices of type 1, -1, -1, 1, and which are positioned accordingly, and then they are summed over. Because that is actually what we will be doing in finite element analysis. We will form a matrix for a single finite element, stiffness matrix. The name is general because though it might be heat conduction problem, but still. And then we will position them accordingly, according to the number of the certain element, and then we will sum them up. And that would produce this global stiffness matrix. So in this case, actually, this is also true. So this is stiffness. So we have a stiffness matrix. It has some, what is inside this matrix is about our scheme, about our finite difference scheme. And this is a multiplier which relates to stiffness. So in general, you can see that we have stiffness times displacement equal to force. In the right-hand sides, we have just forces. But in this multiplier, we have here this distance between our points. So it may look like results might depend on our discretization. Like linearly depend, but it must be not the case, of course. And that's what I would like you to check today. Okay, so I will switch to the next slide, if you don't mind. There is nothing that you probably don't know. Just don't forget this stiffness multiplier after you form that matrix. And we need to fill in the right-hand side. And we need just to solve this set of linear algebraic equations. And by default, in MATLAB, you can always use this ML divide function, which has short syntaxes with this backslash. You can solve this set of equations by calculating inverse of your matrix, by inverting your matrix, of course, and multiplying that by the right-hand side. that is absolutely correct. That's how you would probably do in linear algebra. But this one is coded a little bit differently in MATLAB, so it works more in a more robust way. At least, especially when you have ill-conditioned matrix. So it's better to use this by default, at least, unless you have any special requirement, any understanding why you would need to calculate inverse of your matrix. Okay, so now you solve and you check the result vector. Does it work? Yeah, I'll give you a little bit of time. It's usually required. It's fast to show it when it's written on slides, and it's a little bit longer always to make it work. If you have any questions at this point, please don't hesitate to ask. I'm here for exactly for that. Please let me know if you are finished and we need to move further. I don't hurry you, but just don't want you to be bored. If you want to check previous slide about the matrix, it's here. I don't see that you use precisely this way, because it's just one of the easy ways. Maybe you like more different ways. The point is that you get this kind of matrix, and please check that it's this matrix in MATLAB.
This method, it seems to me like we are calculating all the coefficients of that big matrix by hand, and then we're just simply using MATLAB to do the inversion and multiply so that the display.
Yeah, basically in this case, yes.
But if we want to MATLAB to also calculate all those coefficients, I thought it was what we were supposed to be doing now. So it's a little bit more complicated.
What do you mean calculating coefficients? Which coefficients do you think can vary, and in which situation?
Here, I mean, in a loop of 4,
Yep.
from 2 to n-1, you are giving MATLAB the coefficients already prepared.
Yes.
But I thought maybe we should be using the formula that we gave us, which was about the derivative in the previous one. Yeah.
The thing is that these formulas, they result in exactly those coefficients.
Yes.
So you can think of situation where it would be different. For instance, if you had a bar of non-uniform cross-section, some kind of tapered bar, then it would be different because you would have different cross-section area. This S parameter, it would have different values at different points, and you would have to modify that a little bit. and the matrix, you would not be able to factor out this S outside of the matrix. It would have to sit inside, because it would be different and different laws. Yeah, but this is a quite typical situation. Other than that, for this problem, okay, well, this is our problem. It's always you have these coefficients. There is no need to calculate them, because they come from those equations. So what we are trying to do, we are trying to substitute solving differential equations with solving linear algebraic equations. And what kind of linear algebraic equations we get depends on the particular numerical methods that we use. In this case, we use this central different approximation, and it results exactly in this type of matrix. So you could think about a different way to compose this matrix. That was I was talking about a little bit before. That I'll draw it here. It's not so important that it's not in the video. So how we will be doing it, at least the idea behind in the finite element method in composing entire matrix will be that we will have 4 matrices for each element. And there is no room for calculating anything here. Actually, because of the method that we're using. If we use different methods, we would have to substitute different values here. And then we overlap this type of matrices. And you can see that you get exactly the same matrix. So you cannot directly put those values. You could have formed this type of matrix and then add them up in this manner.
That is what I meant.
Yeah, it's just not necessary in our example. It's just simpler to do. But we will do something like that in the next lecture in finite element methods. And you can modify it by yourself, this code to use. And actually, if you want to consider a tapered bar, like I mentioned, this kind of bar, for instance, with cross-section varying along, a good approach would be to use exactly this type of this way to construct a matrix, because you can then think that for each particular element we have this matrix. And I'll put an asterisk here indicating this. This is the cross section at this point. And for another element, you would have different multiplier here with the same matrix of containing just unity and minus unity. And then you will be able to compose the entire matrix. Okay. So yes, I agree that it looks a little bit that we are just feeling everything by ourselves, but we are solving the equation, and that's our way of solving it. It can be done in different ways. Again, we will discover different ways also a little bit later. Okay, so you solved. Then let's make some simple visualization using this plot function, for instance. Probably the simplest way to visualize how displacements change along the line of our bar. And in order to do that, I will need to add this zero displacement to our vector, because I want to have on my plot also zero displacements at the left end. And if you remember, we did not include it in here. we have the first displacement value in our column of unknowns is u1, which is also already somewhere to the right from this this constraint point. So that resulted actually in this value 2 here in the left top corner, which does not match exactly this situation. That was because of the fact that we did not include this zero displacement in our column of unknowns. That's natural thing to do, to exclude unknown to exclude the variables that you already know, to reduce the number of equations that you need to solve numerically. In this case, it doesn't play any role, of course, doesn't make any difference, just one displacement, but it might be thousands or tens of thousands in more complicated case. Okay, so just to so I extended it here with added this additional value 0, and I made a vector of technically it's not exactly a vector because it's not a column, it's a row. It doesn't matter for this function. You can arrange it in a column, of course. But yeah, so kind of vector of nodal coordinates, an array, one-dimensional array that contains nodal coordinates corresponding to those nodes where we calculated our displacements. Since they were equally uniformly distributed, then I just put it here. Can do it in this way. You can try doing some more complicated, but you will have to change your scheme here, because this multiplier okay, you need to be aware of this h, which still is here, that it will be then different for different sets of points. So it's not very obvious how to do that, and in practice I don't think it's very useful to do that in infinite difference. We will better do that in a finite element method, this kind of change. Okay, so, and just plot, and now what I would like you to do, to run some tests with your code, if it works, and to check that the first check we have already made, that displacements vary linearly. That's what we expected from this type of problem, where we just apply force at the end of the bar and nothing else. There is no body force, nothing changes along the bar, so it can be nothing else. Then what I would like you to do is to check that displacements are not dependent on h, the number of this is the size of our the distance between our nodes, because here in the matrix you see that there is this h, but if we did everything correctly, it must somehow go away during our solution, because the dependence on h must be only in the manner that the accuracy that how we calculate derivatives. In this particular case, that we calculate the real value of the derivative is always the same, so we calculate it precisely no matter how large we take this distance between nodes. So in this particular case, for this first simple problem, it shouldn't make any difference at all. So results should not depend on how many points you take. Please check that run with different number of divisions. And also, please check that displacements are proportional to the force. That what you would expect from a linear nature of the problem. We are using linear elasticity. Where is our bar problem? We are using linear elasticity, and that must result that displacements are results are proportional to the applied force. If you want to think a little bit deeper, I can ask you, what do you think would change if we wanted to solve nonlinear elastic problem, as account for geometrical nonlinearity? Where are those linear elasticity assumptions in our solution? What would change if we wanted to make it nonlinear? There are actually several things that could be different. It's easier maybe to even on this. Where is my initial bar problem? Yeah, it's here. So there are actually those linear assumptions are very deep in this statement. First of all, they are obviously here. That stresses, we assume that they are proportional to strains. In our case, just partial derivatives of displacements. And there is a constant coefficient of proportionality, Young's modulus. That is one assumption. So it may be not this way. Stresses may be not proportional to strains. But actually there is another factor that you cannot see directly from here that was somewhere far away from this equation, is that the very assumption that stresses depend on just those derivatives, it also has to do with linear approximation, linearization. Because this is not the full strain tensor. Okay, this is a very simple problem, just one coordinate, but in general you would have partial coordinates with respect to different coordinates, but it would be still linear with respect to displacements if it's a linear problem, because it's not real strain tensor, and there is an assumption that stresses depend only on this linear part of strain tensor. It has to do with assumptions in linear elasticity, because it might be a little bit more complicated. Stresses might be dependent on a full strain tensor, like if you use a Green Lagrange strain tensor, for instance, or there are some other measures used. There are quadratic terms. So strains, something that produces stresses, may depend not only on this derivative, but also on second order of those derivatives.
You mean even for this 1D problem, there could have been some more order derivatives that are involved?
It doesn't make much sense to make this problem non-linear, this 1D problem. But if you consider this same problem, because how else you can you can deform it? But if you consider if you want to consider it still one-dimensional, but you want to take into account that when it stretches, it becomes thinner. And actually the cross section here, when it became thinner, then the stiffness here is already somewhat lower than it was initially. For instance, if you want to describe this type of effect, yes, you would need quadratic terms as well. Even though it's kind of one-dimensional, but if you want to account that increase, you would be implicitly accounting for transverse displacement as well here, at least implicitly. But probably better to do that implicitly if you want to consider something like that. Okay, so no problems. Everything works fine, no questions. So then I will ask you a question. And that's actually part of your assignment, but you can start doing it now if you feel energy. Okay, it's here. Okay, so let's make this code a little bit more interesting. Something that you cannot right away guess the correct answer anymore. Let's add body forces into this problem. So there might be some physical idea behind that. For instance, if you consider that this is one-dimensional problem, but imagine that this bar is in fact rotating about this vertical axis in the center, in the beginning of in the origin of coordinate, and there is inertia force acting along this. It has some mass and the density and mass, and there is inertia force which stretches the bar because of this rotation. But we are sitting in this non-inertial coordinate system associated with the bar, and we don't care about some other effects that could be associated with that. If we care only about this elongation of the bar, then we could consider that as an inertial force. Or even more simple, if you imagine for a moment that this bar is a vertical bar and you just have gravity applied to it. So it also stretches it. And those are two examples, typical examples of body forces. And how would and we still have some force applied at the end, but how can we account for those body forces in our solution, and how we can introduce them into our finite difference code? Okay, we'll talk a little bit about that, but what I want you to do with that, basically I want you to do that by yourself. There is quite a hint here about how it comes into equation in this form. So it's basically everything I hope you need, but I will help you if you have problems or questions about how to do that. But what I want you to do after you did, I want you to consider that this body force is changing along the bar, so it's not uniform. To make it even more interesting, even less obvious, the solution. Actually, you still can produce an analytical solution for this problem. It's not that complicated, since mostly what makes it so simple is that it's one-dimensional. If it were two-dimensional, it would be much more complicated. But from one-dimensional, of course, you still can, but probably you will not guess the correct answer right away. It will be interesting to look at the results. And I want you to make some simple tests for two types of this dependence of the body force on coordinate. First time is that it's 0 in the beginning, in the origin, and then it increases linearly. Second, what if it's this kind of head shape? So it's 0 on both ends and maximum in the middle, and changes linearly between those points. Of course, first it's better to consider with a constant uniform body force. Kind of more obvious step. I did not put it here. I assume that what you do first, and then I want you to consider this body force changing. And then when you are happy with the results, like, okay, this is reasonable, this contributes, I see contribution of the body force, I see contribution of the force at the end, and I see how the contribution due to the body force changes whether we, according to the way we apply the body force, that is must be not the same. For that you need to adjust some parameters of them, of course, body force, because previous year some students did it so that there was no noticeable change of the noticeable effect of the body force at all, that in the results it was not impossible to see, to distinguish the results with the body force and without it at all, because this force at the end was dominating. So please balance the parameters so you can at least see some influence, otherwise it doesn't make sense. And finally, when you are happy with all those tests and you've mastered these simple central difference methods, I want you to think a little bit about mechanical representation of this numerical scheme. I mean that we took this continuum mechanics problem, problem which is described by parameters that are changing continuously along coordinates. In this case, just one coordinate, but still. But think about if there is any mechanical problem with like lumped problem, with a discrete problem, which you would describe with non-continuous equations right away. Okay, maybe I'm not clear. I don't know, these types of problems, like you have a pendulum, or two elements pendulum, or you have a spring mass problem. So naturally this is like 1 degree of freedom problem. If we allow this mass to move only in vertical direction, this is 2 degrees of problem. And so think about if there is any this type of discrete problem which would produce exactly the same set of equations, this one, as you produced for this continuous problem using central difference methods. And I want you to do that accounting for that for body forces. So what type of problem, if there is any, and there is obviously is some, because I'm asking about that, think about if it's possible to replace your continuous problem with mechanical problems. I want you to think a little bit about that, so you not necessarily need to put it in your assignment report. This is just for you to think about it. Because I want you to give this feeling, this idea that actually numerical methods that we use for addressing continuous problems are somehow equivalent, or at least we can think about them this way. In some cases they are exactly equivalent to replacing continuous problem with some discrete problems.
Can we say, for example, that this beam-like thing is kind of equivalent to the combination of the springs?
Yes, that's exactly what it will be. But I want you to think about parameters. So yeah, it's quite obvious. So it's good that you already have that in mind, that there are some points. I know there are no masses in this case because we are not considering dynamics, but there are some points connected with springs. And obviously those correspond to our nodes. But I want you to think about stiffness of the spring that would produce exactly the same. And maybe there will be some forces applied to those, and how they are connected with the forces that we have in our continuum problems. We have force at the end, and we have some distributed body force inside. So what are the parameters? And yes, it's nice to see that it's possible. And moreover, I want to go a little bit ahead and mention that you can obtain exactly the same system of linear equations by using different method, by using, for instance, finite element methods. At least for this type of equation, there might be some difference in this right-hand side if you have those body forces incorporated. You will see. We'll see that. I think about a little bit about the next assignment. Maybe I will ask you to make this comparison between finite difference and finite element methods. I didn't ask that previous time, but maybe it's interesting. I'll think about it a bit. Okay, so do you have any questions about how to do this incorporation of body forces? What will change in our numerical equations and what must change in our central difference scheme? So basically, I assume that you go to this step and account. So you change equation and you see what changes in this entire scheme. So probably it's not very big secret, and you can probably guess it that I will not spoil it if anything won't be a spoiler. If I think that you have right-hand side in this equation now, and that means that you will have this right-hand side here also, because this after partial derivatives. But please be careful, because we get rid of this denominator here, h squared, taking advantage of the fact that we have 0 in the right-hand side. You won't be able to do exactly that when you have this body force. So that will change a little bit. Be careful with this denominator. Nothing will changes in the in this boundary condition. Nothing changes. We still have this force applied on the right end. But that will change, because that will include something from here also. So these equations will somehow change. At least their right-hand side will change. Yeah, basically that's what is going to change. So there will be the same left-hand side, but there will be right-hand side that is accounting for those body forces. Just make it careful. It's no real difficulty here, I suppose. Just make it careful and make it possible to change this force along the line, so that at different points, spatial points, you have different value of this body force. Okay, so that's basically what I wanted to discuss with you today. I think I will stop the recording now.